Yeah, welcome to a new section in Bioprocess Engineering. Today, we will talk about reactor operations in the batch mode. Yeah, reactor operations, we have three possibilities in a stirred tank reactor. Today, we look at the batch mode, but we will present also the three different modes you have, namely the batch operation, a fed batch operation, and a continuous operation, which is an open operation. All examples are taken from Pauline Duran, Bioprocess Engineering, 2nd edition. It's a wise idea to have a look in this book also. Basically, we have three options to operate them. We can operate them in batch mode, in fed batch mode, or in a continuous form. And what are the specialities? What is the pros and cons? And how can we calculate? That's about it today. So let's start general how these operation modes can look like. So we have the closed batch mode. So the batch mode is characterized of nothing gets in, nothing gets out. If you mean nothing in the case of reactor operation, it always means, of course, if you have an antiform agent getting in, or if you have your base for controlling the pH, that's fine. And of course, air in, out also. Closed means no media components are getting into the reactor. Now, in this operation mode, obviously, you start with an empty reactor, you fill your reactor, you operate it, and then you empty it again and harvest your product. And of course, in between, the volume stays constant. There is no change in volume in this case because you don't put anything in or out. That's clear. If you do that once, everything is fine. Your substrate goes down, your biomass goes up, or your product goes up, and then you can repeat that, of course, for several times. And in between, nothing happens, of course. So, in the other words, the amount of product you can produce or biomass you can produce per year depends on both how fast you produce in your reactor, but also how long is your downtime in between, and the sum overall then gives you the productivity. Now, what about the partial open or fed batch mode? Well, partial open means that you can put something in, but don't take something out. So that's a kind of a summary here. We will go into details what that actually means. In this case, of course, your volume is not constant. So you start filling your reactor until a certain point, then you operate your system, and then you might bring in your media during the operation. How you do that, you will see there are several options. In this case, it's an exponential trajectory, but we don't care about trajectories. And at the end, your reactor might be full, and then you stop your process, you harvest, and that's it. What you can do there is, for example, you can get higher biomass concentrations in the same volume, as an example. However, you also have your downtime. So overall, your productivity is the sum of these productions, and you have to take into account the downtimes. Of course, you can do also intermittent things like this, and then it's a kind of in between a partial open and a fully open mode, but that's just for the sake of completion at that point. Now, the last operation mode is the open mode and continuous mode. So where you bring something in, take something out at the same time. And if it's the same, so the standard operation mode here is that the influx and outflux has the same value. And therefore, in this case, the volume stays constant. Of course, if this is not the case, if you bring in more in than out, for example, you will increase the volume, but usually continuous modes are operated like the same goes in as out. Then you have your constant volume, and you have a certain dilution rate. The dilution rate is simply the volume you bring in per time per volume of your bioreactor. In this case, what you will observe is that you will have a constant biomass concentration and a constant substrate concentration in your bioreactor at the steady state. So you harvest that always, and that then at the end makes your product. There is no downtime in between in a stirred tank reactor operated like this. So this is the operation mode, but now let's have a look in how we can do calculations there. In other words, how can we balance these operation modes? And well, the basic for the calculation in ideal reactor is simply an unsteady state mass balance of a component I in an ideal reactor. So in other words, if you just in words, how can you balance that? The change in the mass of your substance component I is, of course, if you add something here, you will increase it. If you remove something here, you will reduce it. And if something is being produced, you will increase it. So inflow minus outflow plus production is the mass change. And of course, you can write that as a differential equation. It's very simple. It's the change in the mass over time. And then you have your inflow, the flow rate in, for the concentration in, the flow rate out for the concentration out. And here you have your production or consumption rate for the volume. And at the end, you get this equation. And this is basically the same as we have talked about in balancing stuff. Okay, so this is the equation we use as a starting point for everything. And now let's come how everything looks like in a batch operation. So we have already done some calculations, but today in reactor operations, we are more at the side. How much can we produce, for example, per year? So we want to have the production time. So let's look again at this mass balance and deduce quickly our, for the biomass at least, what is our production time. So here we go. Okay, so we start here with our mass balance we have deduced before. And now let's just look again what happens if we look for the biomass. So in the case of a closed system, so we talk about a batch culture. Of course, we say it's dx dt is equal to, that's 0. Nothing gets in, nothing gets out, again 0, plus the reactor volume for the rate of production of the biomass. And as we know, the rate of production of the biomass is mu fold x. So, and putting this inside, we have dx, it's a large x, dt is equal to v fold mu x. And now let's get ahead of this volume, and for v is equal to constant, which is of course the case in our batch culture, we can write v dx, the small x, as the biomass concentration, dt is equal to v volume fold mu x, and then we can simply kick out the volume. First of all, we have dx dt is equal to mu x, and now we can write that as integral x0 to x dx divided by x is equal to, we separate the variables, integral 0 t mu dt. And now for mu equals mu max equals constant, which is the case in a batch culture. You remember that according to Monod, the specific growth rate is constant, as we have usually a substrate concentration which is way higher than Ks. So this is almost always true in a batch culture, and the very end doesn't matter too much because that's then so fast reached that nothing will change. So then we can take, we can write it like that: x0 x dx x is equal to mu fold 0t dt. Okay, and now we can of course integrate, and we get ln x0 minus ln x is equal to mu t. And then we get of course our x is equal to x0 e mu t. So that was our equation describing how biomass growth in the batch culture. So how long does it take now? Now the batch time, if TB is our batch time, TB is the batch time, then we have our final concentration, X final. We have our initial concentration, X0 is E to the power of mu Tb. And then we simply solve that. And then we have, of course, XF divided by X0. So we bring it over there. And then we do it ln. And then, so it's divided X0, ln. And then we have ln XF divided by X0 is equal to mu Tb. And therefore, of course, Tb, just separating, just bringing the mu over there, is 1 divided by mu fold ln X final divided by X0. So this is our batch time in the exponential phase. Of course, sometimes you have the lead time and so on. This is not acknowledged here. So again, as we have already deduced in the section growth kinetics, we came up with the equation X is equal to X0e mu T in describing the growth of the biomass in batch culture and having two assumptions. The volume is constant, which is of course the case in a batch system, and the specific growth rate is constant, is mu max, which is also the case in batch culture, as based on Monod, the biomass, the substrate concentration is way higher than Ks. And simply by solving it to Tb, we came up with this equation 9 here, that our batch culture time is our final biomass concentration divided by X0, ln divided by mu max, and then we have it. So it's very quick. And it's quickly deduced. For the exam, it's important. It's in your formulary. Don't deduce all equations for the exam. You should know where it's coming from. But of course, take the equations from the formula. It's just faster. Don't lose time with that. Okay, so you can do a similar approach with a substrate uptake. And then you end up with this equation. And you see here, this starting point comes also from kinetics, and we have here our growth-related term, our maintenance-related term, and our term which comes from the product formation, which is only the case if we have a product formation which is not associated to the energy metabolism. In this case, we can also solve the equation, and we can calculate what is our batch culture time, and we end up with this equation. It's simply solving this equation. And finally, we can do the same for product formation. And again, here we talk of product formation irrespectively of its mode of generation, and we end up with this equation. Of course, also this can be deduced from what we have learned in kinetics. So this is, we have now three possibilities of calculating our batch culture time, either based on the biomass, the final concentration, either if we say I want to reach a certain substrate concentration, or if I want to reach a certain product concentration. So of course it depends on what your intention is, and like that you will then calculate correspondingly use the appropriate formula and simply calculate your batch culture time. Now, of course, this is just the time, as I said at the very beginning, this is just the time what is needed for the growth. But in addition, you need to harvest, you need to pump everything in and so on, and you need to clean. And of course, this adds up to the total batch time. And we have here our total batch reaction time is simply our batch culture time plus our downtime. And the downtime is the harvest time, it's the filling time, it's the lead lag time, which in this case includes the filling time, and it's the preparation time for cleaning, sterilization, and everything. So here on this chart you see it, and of course that this is just what we have calculated now, the batch time after the lag phase, and the remaining times need to be taken into account. And this gives you then your total batch reaction time. And this at the end gives you the amount of batches you can, for example, produce per year. If your total batch time is 24 hours, ending up with your batch time of 5 hours plus 19 hours downtime, you can, of course, just produce 365 batches per year. And now let's have a look at an example. So an example is we want to calculate the batch culture time of Pseudomonas mobilis, which is used to convert glucose to ethanol in a batch ferment under anaerobic conditions. So here we are. The yield of biomass from substrate is 0.06 grams per gram. You remember, don't cut out the grams. Yield coefficients could be molar coefficients or mass coefficients. And if it's gram per gram, you know it's now a mass yield coefficient, which is the general thing. Maintenance coefficient is given, and the specific rate of product formation due to maintenance is given, and the maximum specific growth rate is given. And we inoculate 5 grams of bacteria into 50 liters of medium containing 12 grams per liter glucose. And what we want to know is, what is the batch culture time required to A, produce 10 grams of biomass, B, achieve 90% of substrate conversion, or C, produce 100 grams of ethanol. Now, of course, you should do your calculation on your own. We will do the solution together, but please now pause the video and try to calculate it. Basically, what you have to do is just use the formulas we have talking about a couple of seconds ago. And of course, now then we will do the things together. So please pause and try it yourself first. Okay, so here we go. So you have already tried the calculation yourself, of course. Now we just check it, whether you were correct. So the first thing to do is always we take the things which were given and bring it to the first thing we do is just transfer the information and put it in the general way to present it. So we had our biomass yield, its YXS, was 0.06 grams per gram. Substrate concentration initially was 12 grams per liter. And we were set that our X0 is 5 grams in 50 liters. Don't forget that you want to have concentration, so therefore it's 0.1 grams per liter. Okay, so now we have simply transferred all the informations on this presentation, and now start with A. So we want to have as a production target 10 grams biomass. So in other words, X final is X produced plus X0, 10 grams in 50 liters plus 0.1 grams per liter, which is already given. So we end up with an X final of 0.3 grams per liter. Don't forget that you need to convert that into a concentration, and don't mix up concentrations and total masses. So your final concentration is 0.3 grams per liter. And now we simply use our equation number 9. TB is equal to 1 divided by mu max fold ln X final divided by X0. And if we put our values here, we have 1 divided by mu max is 0.3 per hour. 0.3 per hour fold ln. Final concentration is 0.3 grams per liter divided by 0.1 grams per liter. Of course, that gets kicked out. At the end, you will have hours. That's a good thing. And then you put everything in your pocket calculator, and what you should get at the end is 3.7 hours. So this is our batch time, which is needed to produce 10 grams of biomass. Now we come to part B, and the question is how much time is required for 90% substrate conversion. And obviously the final concentration in this case is simply S final is equal to 0.1 fold S0. Our S0 is 12 grams per liter, so it's 0.1 fold 12 grams per liter, and therefore it's 1.2 grams per liter. And we now simply look in our formulary and we get the equation 11, which is giving us the batch time as a function of the substrate concentration. And we just copy it. TB is equal to 1 divided by mu max. Now, here we have the production of ethanol. So product formation is coupled to energy production directly to ATP formation. And as you remember, then we have this growth associated term. We have this maintenance associated term where we have the substrate shuffling in, but we have not this term here, which is not connected to growth product formation, which is not connected to energy production. So therefore we just have this term and this term. Don't forget that to kick that out. And this makes life easier because we have no QP given, we have no YPS given, but as you see, all other parameters are given. So we can simply go now with our calculation. And of course you have the parameters, we have copied them already. So TB is equal to 1 divided by the mu max is 0.3 per hour fold ln. And then we have 1 plus S0 is, as we have calculated, 12 grams per liter, as it's given, 12 grams per liter. And SF we have calculated is 1.2 grams per liter. And then we divide. We have 1 divided by YXS. YXS is given and it's 0.06 grams per gram. And then we have our maintenance due to substrate consumption. It is given as 2.2 grams per gram per hour. And we have our mu max, which is still 0.3 per hour. And we multiply everything with x0, which is 0.1 grams per liter. Then we check. We first kick out now these grams per grams. And we kick out the per hour. And we can also kick out the grams per liter. And that's fine. Then we have nothing in the ln. And this gives us the correct unit. And if you put everything in your pocket calculator, we end up with a TB of 5.7 hours. And the unit is correct. No units in the ln left. And we just have this divided by hour. So in other words, the batch culture time to achieve 90% conversion is 5.7 hours. Now let's come to C. We want to produce 100 grams of ethanol. So in this case, we simply take our equation number 12, and this equation is irrespective of the way of formation. So it means that it doesn't matter whether it's energy related or not. So let's just put equation 12. And of course, we have our final concentration. We have 100 grams ethanol. So in other words, our P final is 100 grams divided by our volume, which is 50 liters. So we end up with 2 grams per liter as a final concentration. QP is not given. However, it's no problem to calculate it. In this example, product formation is coupled to ATP synthesis. And therefore, we can take equation 22 from the kinetic section. And this is simply QP is equal to YPX fold mu plus MP. So this was this equation 22. And the good news is now everything is given. So we have QP is equal to YPX is 7.7 grams per gram. Fold mu, it's 0.3 per hour. And MP is 1.1 per hour. And in total, and we end up with a QP of 3.4 per hour. And then we can start. Therefore, TB is equal to 1 divided by 0.3 per hour fold. ln 1 plus, again 0.3 per hour, divided by x0 is again 0.1 grams per liter fold. Our QP is 3.4 per hour. And altogether this P final minus P0. P0 is not given, and it's of course 0. We don't start with ethanol, so it's just the P final, so it's just 2 grams per liter. And if we put everything in our calculator, first we check, of course, the units. So we have here the hour is disappearing, the grams per liter is disappearing, and we end up again with hours as a unit coming from this one, which is good. So always check whether the units are okay. And we end up with 3.4 hours. So that's it. Now we have the solution. So thank you very much for your attention to the how to calculate batch times in batch mode, how to set up the equations in batch mode. Looking forward to seeing you next time. Have a nice day.